This seminar. It's a real pleasure to me to introduce today Gemma González Torra. She is postdoc working at the EMI Nodal Research Group on stellar atmospheres and mass load, led by Dr. Andreas Sanders, at the Astronomisches Röntgen Institute, University of Heidelberg. She did her PhD jointly at ISO Garchim and Liverpool John Moore University, where she developed a model to add the stellar wind contribution to the extended atmospheres of red supergiants using interferometric observations. And at present, she is working on a spectroscopic analysis of OB and Wolf-Rayets stars using stellar atmosphere models. So you see already that she has been covering a wide range of type of massive star object. And she's also very interested in studying the interplay between massive stars and their host galaxies. Recently, she has been awarded one of these early career visitor program grants offered by the Instituto Astrofísica Canarias. And it's interesting that she is the third one in the third one early career research in the massive star community who has been awarded one of these grants, since we have also Joel Keseli and Julia Bodensteiner. She arrived 2 weeks ago already, so she has been enjoying a lot being here at the IC and also enjoying Tenerife. And she will be here until 20th of December, so still 1 month more. So I'm sure she will be happy to discuss with you if you find interesting what she will be presenting today. So whenever you want, Gemma, the floor is yours. Thank you.
Thank you very much for this very nice introduction. So as Sergio said, I'm a postdoc at Heidelberg University right now. And what I'm going to be talking about today is basically my scientific contribution to modeling the stellar atmospheres of massive stars. So first of all, what are massive... Oh, wait, but this was working before. Okay, well, Yeah, sorry. Okay, now it's working. So first of all, what are massive stars? So massive stars have initial masses greater than 8 solar masses, and they are actually very important for almost all branches of astrophysics. So first of all, they are the main source of stellar feedback to their host galaxies, which means first that they have through their very strong winds, they actually chemically enrich their host galaxy, and they also have really high and strong ionizing radiation, which also will ionize their ISM and their surroundings. Then these stars, as they evolve, and at the end stages, they produce elements with higher masses than iron through their R and S processes. And then the stars, as they die through supernova explosions, these explosions will also enrich their surrounding. And these supernova explosions can also be used as standard candles in order to get the Hubble constant. So they also have applications in cosmology. And we also know that massive stars, they mostly come in pairs, so they come in binary systems, and they have also merging processes. And then we can also study the gravitational waves. So as the stars die, we're going to have the remnants, which are compact objects. So we're also going to get black holes and neutron stars. And then some of these very massive stars, they even have really energetic processes, which means that they eject gamma, such as gamma ray bursts, which are also interesting for high energy astrophysics. And the stars are also interesting for cosmology because we know that at the universe, at the beginning, we have the neutral hydrogen at some point, right? And then this neutral hydrogen got reionized, and that's why now we have our galaxies. So through this reionization era, there must have been some sources that had very strong and very high energetic photons that were able to reionize this neutral hydrogen. So we think that some of the sources could be actually population 3 stars, which are the most massive and the first stars that we got formed in our universe. And these stars have zero metallicity. So as you can see, massive stars have a lot of implications for a lot of branches in astronomy. So now going a little bit more deeper into the massive stars, here we have a Hertzsprung-Russell diagram where we see the temperature increasing from right to left, and then the luminosity also increasing up. And as you can see, this is a HR diagram already for massive stars. So we already made a cut here to like 1,000 solar luminosities. So since these stars are very massive, this means that they will burn a lot of energy, and this means that they will actually end their lives really fast. So compared to the sun is going to be around 10 billion years in the main sequence, while a massive star will be only 20 million years. And the more massive, the less time it will spend in the main sequence. So these stars, they have very different evolutionary stages, right? So we have first the OB main sequence stars, which are stars in the main sequence that are burning hydrogen. Then as we start depleting this hydrogen, the star will evolve into the right side of the HR diagram. It's going to get bigger, and the effective temperature is going to get colder. Then we're going to get the supergiants. So we go from blue to yellow and then red. And the red supergiants are the coldest massive stars we have, and they are highly convective. But it can also be that through this process of evolving, we have strong mass ejections, and then we can also eject part of the mass of the star, and we can eject the convective layers, and then we're going to be seeing the inner layers of the star. So as we get these inner layers, of course, the temperature in the surface will increase because we're seeing the interior, and then as it increases, it will move back into the left of the HR diagram because the temperature is increasing, and we're going to have other types of stars like Wolf-Rayets. But I'm going to be talking about this more in detail later. So what do we do to observe massive stars? Well, the typical, right? We get the photons that we get from the photosphere and above, and then we get them either photometry or spectroscopy. So we have an idea of the elements in the atmosphere of the star. And in order to study the stars, we need then models to fit our observations. So how do we model the atmosphere of a massive star? First, we have an interior that we do not model the interior, so we have a hot opaque interior. And then there's the photons that are coming from the interior of the star. They are going to interact with the atmosphere. This process is happening there. And then since we have a lot of processes happening, what we do is some approximations. First of all, we assume that the star is spherical, which is a pretty decent approximation. And then we also use, in our case, only one dimension to make it easy. So then this atmosphere ejects there's some material that's flowing in a steady wind. So we also have the stellar wind, which is ejecting the material. And then for this, we also assume a constant outflow of material. So we have another simplification, which is that we assume the model to be stationary. So how do we model then these winds and then these atmospheres? Well, it depends on how evolved the star is. We have 3 different regimes, and are the ones that I'm going to talk about today, because this is the work, like the regimes that I've been working on, which covers almost the whole HR diagram. So first, we're going to talk about red supergiants, and this is because for my PhD, I started working on red supergiants, so we're going to go chronologically to what I've been doing. And you will see that red supergiants are super complicated, so then we're going to move into relatively easier modeling, which is the OB stars, which are hotter. And then finally, I'm going to talk about the Wolf-Rayets stars. And then at the end, I will explain how these stars and how the stars and they react with their surroundings, and they interplay with these stars and their host galaxies. So let's start with red supergiants. As I said, red supergiants, they are highly convective, they are evolved stars, they've been on the right of the HR diagram, and they are very cold. So when we see a red supergiant, we're going to see something like this artist representation here in the middle. So we get the photons from the photosphere, right? This is this red dot. Then there's a stellar wind, so there's this material being ejected. And the problem is that we don't really know the physical processes that are triggering this stellar wind. And since we don't really know these processes, when we model it, usually we leave it empty because we don't know how to explain it. So then there's this material that's being ejected, and at some point the material gets colder in order to condense into dust. So we're going to also have a dusty shell around the red supergiant. So as I was saying, the triggering of the stellar wind is not understood. We're still missing ingredients. So what we do for our models to model the atmospheres is we model the atmosphere up to the photosphere. Then there's this wind that we don't know how it works, so we leave it empty. And then we artificially add the contribution of the dusty shells. The problem is that in this extended atmosphere, there's of course a lot of things happening, right? You can see here, this is a schematic representation. Here we have the star, the photosphere, there's this extended atmosphere where there's things happening, there's gas there, right? And then we also have the stellar wind. And the dust gets formed at around 800 Kelvin, so around here. The thing is, in this region that we leave empty, there's molecules that are being formed. And these molecules, they will contribute to the spectra that we are observing, right? So if we are not modeling this region, the molecules such as the titanium oxide bands or the CO bands, we're going to underestimate the strength. So we cannot leave this region empty. Also, then, in order to estimate the mass loss rate of red supergiants, right, what we do is we observe the dust. So we model the dust, we get the dust excess, and then we get an estimation of how much mass is being lost of this star. So the thing is that modeling the dust has a lot of uncertainties, and specifically for the gas-to-dust ratio, this is a highly uncertain parameter. And when we're trying to get the mass loss rates using dust, we get mass loss prescriptions for the same star that can vary by an order of 20. And this is very problematic because depending on the mass loss that we're getting, we can have that our star is not going to explode a supernova or our star will explode. So this is actually very controversial, which means we need to find a way to get the mass loss rate which does not rely on dust. So why not model then this extended atmosphere, right? So in order to model this extended atmosphere, we cannot just look at the spectra, because if we look at the spectra, we're going to have the whole integrated light, and we are losing the spatial information, right? So what we need is really high angular resolution in order to see what's happening here. And for that, I used interferometry. So interferometry, the advantage is that it's giving us high angular resolution measurements of stars. So as you know, interferometry is using an array of telescopes in order to increase the effective area and then increase the angular resolution. So what we are observing then is the visibility of light, so this interference pattern, right? And this visibility is the Fourier transform of the intensity. So basically here it gets more complicated because there's some more math in this observation technique. But then we have interferometry, And then we get our model, and then we compare it. So for the models, we use the initial models up to the photosphere, which are the Marx models. These are the models that are now typically used for red supergiants and for cold stars. And then what we do is we include this contribution of the wind up to 8 stellar radii. And you can see it here in the density. So for this, we use the normal mass continuity equation, which is also used for hotter massive stars, right? And then we can fix our mass loss rate. We know the radius, and then we either need the density or the velocity profile. So for this, we are using a density profile that's prescribed, so it has this shape, and this is based on observations of Betelgeuse. And then we also need a temperature, right? So for this, we are using 2 different temperature profiles. The first one is just simple radiative equilibrium, which is just the temperature decreasing with radius. And then we have this other one here, and you can see there's a temperature inversion, which is the temperature increasing, and this is because of the chromosphere of red supergiants. So we get our models, we solve the radiative transfer equations, and then we can get the flux, so we can get the spectra, but we can also get the intensity with respect to the line of sight. And doing the inverse Fourier transform means that we can also get the visibilities, right, which are these observables that we are getting from interferometry. So this is what you see here. You have the upper plots are the spectra. In gray, it's for a red supergiant. This is the data. And then the lower plots are the visibilities with respect to the wavelength. And to interpret the visibility, basically, it's giving us an idea of how extended our models are, right? So you see here, in red is our model, and in green is the initial model that we are using. And we can, for the very first time, actually reproduce the visibilities and reproduce the extension of red supergiants. And this is something that's never been done before. As you can see, actually it gets so much better when we use our models. So why is this important? This is important because, first of all, well, now we have finally a model that we can use with some extension of the atmosphere, and also because then we can get a mass loss rate. Because in order to estimate this extension, we need to get a mass loss rate, right? We need to estimate this mass loss rate. So this is giving us a way to get mass loss rates, which does not depend on dust, and it does not depend on uncertainties. And then it's another reliable approach to get mass loss rates, which is actually super exciting, I think. So this is the conclusion of the first part, cold stars. What's the conclusion? Well, these models are the least accurate because we don't understand the physics yet, so we need to do some more work on the physics. And while we don't understand the physics, what we can do is we can help ourselves by using observations. So for instance, using interferometry. So now I want to go into hotter stars, which are a bit easier to model. And why they are easier to model? Because we know what's driving the wind for these stars. So we know, what's driving the wind is radiation, so the photons that are coming from the interior of the star. They are gonna interact with the atmosphere, and then they will either get absorbed and then they will get re-emitted at a random direction. But since we have all these photons coming from the radial direction, so coming from the inside of the star, and then they being re-emitted, in the end we're gonna have this net momentum on the radial direction. And this net momentum is gonna create an acceleration, and it's gonna drive our wind. So basically what we need to estimate is the radiative acceleration. And for this, we're using this Eddington parameter. And you can see that this parameter depends on the luminosity, on the mass, and then on this kappa factor here, which is the opacity. And I guess everyone knows what the opacity is, right? But just very quickly, if it tells us how opaque our medium is, right? So if the opacity would be infinity, this means that at that wavelength, all our photons that are coming from the interior of the star, they are all getting absorbed, so we're not observing anything from in the interior. And if the opacity is 0, nothing is being absorbed, which means we're getting the photon directly without interacting. So from 0 to infinity, that's what we have to find out. So what are the processes that contribute to this opacity? So we have, this is very basic, right? If everyone, I guess everyone knows, but just in case, we have the different radiation processes that we can have from photons interacting with the matter, right? And here I want to, is this mouse? Sorry. So here, oh, it's not moving. Anyway, I want to focus your attention on the bound-bound transitions. These transitions are when the photon is interacting with a bound electron in an atom. This electron will catch the photon, it will go up one energy level, then it would go down, and then the photon will be re-emitted. So this gives us a source of opacity, and for these OB stars, this is the main source of opacity that's driving the wind. That's why we call these stars line-driven winds. So now we know the sources of opacity. What we need is our model. For this, we are using the Potsdam Wolf-Rayet atmospheric models, the power models. And these are 1D models, and they work in a way that we have our input, which is the stellar parameters, so the temperature, the gravity, the luminosity, then the abundances, and then we can also input the parameters of the wind. This is the mass loss rate that we have and the velocity of this wind. In this case, if you remember, for red supergiants, we said we prescribe the density. In this case, what we're doing is prescribing the velocity, and it's the so-called beta law. So we do all this. We start running our model, and then this model goes through an iterative processes. In this case, we solve the temperature stratification, so the model gives us the temperatures, and then we also have to get the population numbers in our elements, right? So for this, we need to solve the statistical equilibrium equations. So we also then solve the radiative transfer, and finally, after hours and days and a long time, we get our spectrum that we can compare with the star. So this is for 1D modeling, right? But right now we have some new multidimensional simulations. So that also can give us insights on these O stars. So for O stars, we actually have a collaboration with scientists from the group of Leuven that they are working on multidimensional simulations of the atmosphere of these stars. So what they do is, well, they have different approximations, right? Instead of doing the whole spherical star, they do a box in the star, they solve the radiation hydrodynamical equations, and then they also don't solve the whole population numbers and statistical equilibrium because that would take super long, so they are using local thermodynamical equilibrium approximation. So they do this for different spectral types, O8, O4, and O2, and you can see here we have the velocity, the density, and the temperature, and these are time-dependent simulations. And then they have different snapshots, and in the end, they do an average, which is the red profile that you see here. So here you can see what they model is this dashed orange line is around the photosphere. They go from a little bit inwards the photosphere, so the subsurface layers, and then they also model the outer part, so the wind. So what they found out with these simulations is actually that in the inner part of this photosphere, or of this atmosphere, sorry, you see that there's a lot of iron, and this iron is gonna get the photons that are coming from the interior, and then there's gonna be a lot of different line transitions of iron. And this is the so-called iron opacity peak. And what happens when the opacity increases? As we've seen, actually, the acceleration increases a lot, which means that this area, like around the subsurface layers, due to the opacity peak, it's super unstable because there's a lot of acceleration happening. So this means that there's a lot of turbulence in that layer. So this is something that we don't see with our 1D models, but we can model this effect with our 1D models. And that's actually what we're doing with this collaboration. We're learning from the multidimensional models to improve our 1D models. So we can include the effect of a turbulent pressure. And then we see here, we compare our 1D models without turbulence and with turbulence. And here you can see the average 2D profiles. That's what I was showing you for the density for the different spectral types. And you see that the model without turbulence can really not reproduce well what we're seeing from the multidimensional simulations. But when we include a turbulence, we can actually reproduce so much better the density profiles. And this is actually really exciting. But what happens with the spectrum, right? Because including a turbulence is going to change the pressure scale height, and then it's going to change our lines. So we can also see what happens with the spectrum. This is the model without turbulence. And then when we add a turbulence, we can see that actually the lines change. If the line change, this means that in order to fit the width of this line, it's narrower, which means that we're going to get a different surface gravity, which means we're going to get a different mass in the end. So that's what we try to do. We get our model with turbulence and a fixed surface gravity, and then we try to fit the width of this line with a model that has no turbulence. So we have to change the surface gravity, basically. That's what you see here. This in green we are fitting the width of the lines, and we see that we obtain two different surface gravities. So why is this interesting? This is interesting because right now, all the models that we are using to fit our observations are 1D models, and they are models that do not include turbulence. So when we fit a line in our observations, we're going to get something like this with a certain surface gravity that's going to give us a certain mass, right? But if we include a turbulence, we're going to get a different surface gravity, which means we're going to get a different mass. So the masses are changing here. And this is interesting because we think, well, you can see here how the masses change by changing the turbulence and fitting the same line. So you see that actually it changes a lot, it's like more than double. So this is interesting because this is a so-called mass discrepancy, which was found by Artemio here. And this discrepancy is telling us that the spectroscopic mass that we get from our observations and from our stellar atmosphere models is not the same as the mass that we infer from the evolutionary models. So when you check the ratio, you see that the evolutionary models usually give us a way higher mass. So with our models that have no turbulence, we get this ratio. But when we include the turbulence and we are increasing our mass, then the mass discrepancy almost disappears. So this is actually really cool because just by including the turbulence, not only we are in accordance with multidimensional simulations, but we also can fit and we can solve this mass discrepancy. So this is actually the reason why I'm here, because as conclusion for this part, we know we can learn a lot from comparing multidimensional simulations and 1D models, and we know that if we include the turbulence, we are gonna get closer to what the simulations are saying, and we are also gonna be able to maybe solve this mass discrepancy. So far this is all based on models, as you know, but what we're doing here at the IAC is actually working a step further. So we are using the IACOP database from Sergio, which has a spectra, high resolution spectra of O stars. And then what we're trying to do is we're fitting the stars first without turbulence, and then we include a turbulence, and then we get a different log G. And then we see what happens with the masses. And we compare these masses with the evolutionary masses. And then we want to see and find out if actually this mass discrepancy is solved or not. Okay, so now I want to talk about Wolf-Rayet winds. Yeah, I think it's also really interesting. So first of all, what are Wolf-Rayets? So Wolf-Rayets, they were initially just a spectroscopic definition. So when you see a spectra that has super strong emission lines of a star, then you see that you're actually observing a very dense and hot wind, which means that for the so-called classical Wolf-Rayet stars, we have a massive star that rejected a lot of their material, as I was saying, right? And then we are seeing the inner layers, the very hot and inner layers. So this is the definition of the Wolf-Rayet, and we have different spectral types as what we have with normal massive stars, right? So depending on the emission lines that we're seeing. There's the WN Wolf-Rayets, which have basically nitrogen. So there's the WNs have nitrogen and helium emission lines, but there can also be stars that have some hydrogen, and this means that they are still burning maybe some hydrogen in the core, and these are the so-called WNH. These are a bit less evolved. And then we have, when there's no hydrogen at all, these are WN stars, and we know that they are burning helium in the core. So there's also some sub-classifications, right, as all the other stars, so with different numbers depending on how hot they are. We have the early ones, which are from 2 to 5, and these ones are hotter and they have higher ionization lines, like nitrogen 5, for instance. And then we have the later ones, which are colder, and they will have like nitrogen 2 or nitrogen 3. So this is for the WN stars. Then we can also have WCs, and probably you guessed it right, that's because they have carbon lines. And then WOs that have oxygen lines. And these also have helium, but they have no hydrogen at all because we think that these ones are more evolved and they are not burning hydrogen in the core. So this is for the types of Wolf-Rayet stars, but how are these stars formed and how do these stars evolve? So we still don't know. This is still very uncertain. There's the so-called Conti scenario for galactic metallicities that says that these stars, they started from a massive O star in the main sequence. Then the star ejects a bit of their mass. We start getting some emission lines. So there's the OF. And then it ejects more of its of its material. Then we have the W and H, then WN, WC, and WO. So we have a nice transition, and we burn from burning hydrogen to burning helium in the core to carbon, etc. So this is very, very uncertain because right now in my group, they found actually a star that goes from WN to WO, skipping the WC. So it goes directly from N to O. So actually, and it can also be that these stars are not only formed from O stars, they can also be formed from like post-red supergiants, as I was saying, right? It can be that the post-red supergiant emits a lot of the material and then it gets hotter and we also get a Wolf-Rayet. But as I was saying also, we found this WN/WO, which is skipping the WC. So we still have very uncertainties on how these stars evolve and they are formed. And I have not much time to talk about this, but I can totally talk about this at some point if people are interested. So what are the challenges of modeling these stars? Well, these stars are very dense, right? We're modeling very dense and optically thick winds, and the lines are formed in these optically thick winds. So the problem is that actually just using a prescribed velocity law, as I was saying earlier, so a beta law, this doesn't work because this breaks the hydrodynamic equation and we don't have the equilibrium. So you can see it here. If we are using just a prescribed law, we cannot be hydrodynamically consistent for the Wolf-Rayets. So what we have to do is we need to solve the whole hydrodynamic equations in order to be consistent, as you can see it here. So of course, this adds an extra layer of time and it takes a while, but the advantage is that we actually know more about the physics of the star because we're not just prescribing the velocity, right? So we are actually solving it hydrodynamically. So we can actually understand what happens in the wind. For this, we have a new branch of power. So this is the so-called hydrodynamically consistent model. And instead of inputting the wind parameters and prescribing a velocity law, we are solving the hydrodynamic equation. So the problem is that these models, they would take way longer, so they can take weeks or months. So we are actually making less approximations, we are learning more about the physics, but the computational time increases, right? So these are the 1D models, but what happens when we compare again with the 3D simulations? So we did the exact same thing that we had for the B stars, and these are simulations of Wolf-Rayet stars. And then now what we are doing is we are comparing the hydrodynamical models, right? So you can see, this is the same, the average profile of the velocities, the densities and the temperatures for the 3D models compared to our profiles with the 1D models that are hydrodynamically consistent. And you can see that in this case, actually, since we're learning more about the physics, our models are in accordance, especially if you check the densities, the models are well in accordance with the 3D simulations, which is really great and very reassuring. So now what I'm going to talk about is an application, so the interplay within these stars and their surrounding. Because I guess there's some people here that are doing high redshift galaxies or ISM, and they are going to be telling me, okay, Gemma, this is really cool, but this was very specific, and like, why do I even care about this if I'm someone that's looking at high redshift, right? So, well, the stellar atmosphere modeling is not only useful to get the analysis of the star, but it can also give us a lot of insights on the ISM and the host galaxy. How? So here, this is some other work that we've been working on in a collaboration with ISM experts and us, stellar atmosphere experts. And basically, it started from the motivation that when you have high redshift galaxies and low metallicity nearby dwarf galaxies, you get some very strong nebular emission lines. And for instance, the helium-2 4686, you see these lines in these different galaxies and when we get the integrated spectra. But in order to have this helium-2 line, what we need in the galaxy is sources that have photons that have high enough energy in order to produce these lines, right? So the problem is that when we compare these observations with population synthesis models, so what the models are telling us, we are actually not able to reproduce this line. So the models are missing ingredients, they are missing something. And what are the ingredients? As I was saying, we need sources that have very high energy photons. So in particular, to produce helium-2, they need to have wavelengths less than 228 Armstrongs. And this is emission in the extreme ultraviolet, right? So what about massive stars? Massive stars, if they are hot, of course, they would have some emission in these wavelengths. So for that, we use atmospheric models because we cannot have observations of extreme ultraviolet for these stars because they are super obscured, right? But when we use atmospheric models, we can actually have an idea of how this extreme ultraviolet would look like. So there's the spectrum in this region, and then we try to get the number of photons per second that we have of a certain energy in order to ionize helium-2. So this is then the photons that have a wavelength that's lower than 228 Armstrongs. And we estimate this number of photons. You can see there's an example of a massive star, but as you can see, the number of photons is pretty low, so it's quite negligible, so we're not seeing here anything. But what happens when we start checking Wolf-Rayet stars? And specifically when we check earlier WNE stars. So you can see at low metallicities, these stars actually produce a really high number of ionizing photons. You can see it here, it increases a lot. And then they're actually really good sources then of these ionizing photons to produce the helium-2 that we are seeing in the nebular emissions. However, right, so this is great because if we find these stars in these galaxies, then we know that, and then if we somehow put them in the population synthesis, then we found the missing ingredients, right? Because so far in our population synthesis do not include these stars. So there's two problems. The first problem is that the population synthesis, they don't include the stars because the evolutionary models, they don't know how the stars are formed at low metallicity. So why? Because these early WN stars, they are really hot. They have effective temperatures of 100 kilokelvins. This means that if they are really hot, we're seeing very inside the star, right? So this means that we must have had ejected a lot of this material. To eject this material, we need very strong mass loss. So the mass loss that we're having is actually not that high. So if we assume that the star is just stripping material, we cannot explain how the stars get so hot, and we cannot explain these WNE stars at low metallicities. Then another option would be to have binary systems, right? So, but we have more and more now work that's saying that most of these stars, they don't have companions. So binaries also don't help. So we don't know how they are formed, and we need to use then other ways to form these stars, maybe through some like homogeneous mixing, and there's some theories, but we still are not really sure how the stars are formed in low metallicity. And since we don't know how they are formed, we don't reproduce them, which means we don't have them in our models. So, okay, but at least if we could see them in the observations, then this would give us an idea that they are there, right? So, also I forgot to mention that these models already fail for like SMC metallicities. And for the SMC, we know that there's WNE stars, so we know that they are there. So we have to find a way to reproduce them. So if we would detect them in the integrated galaxy spectra, then we would at least know that they are there. Okay, but there's another problem. It's how we detect these stars. Usually what we do is we detect the so-called Wolf-Rayet blue bump, which is this bump that you see here in the spectra of the galaxy, and it's due to the helium-2 and some nitrogen lines. And when we see this bump, this broad bump, then we can say that there's Wolf-Rayet stars. The problem is that there's a significant number of star-forming galaxies that they have very strong nebular helium emission, but we do not see a bump, so we don't detect the stars. So does this mean that the stars are not there? Or does this mean that the stars are just hidden? So this is the work that we've been doing now with a collaboration with the local volume mapper observations, which is an integral field unit. So what we do is we go closer, right? We go to the best solar metallicity laboratory that we have nearby, which is the SMC. So the SMC is great because we know there's a population of W and E stars. We can resolve them and we can get individual spectra of the stars. And then what we do is we compare them with integrated regions around the star using this integral field unit. So this is basically what we do. This is a zoom in of one of the stars. The stars would be in the middle, and then we are getting different apertures with this local volume mapper, and then we are integrating the whole spectrum, and we're comparing them with the individual star. So this is what you see here. Here you see in the upper plot, there's the normalized flux, and this is, of course, the 4686 helium-2 line, which is the strongest line in this optical for these stars. And then you can see here in the star, there's this broad emission, right? And then when we check in different shades of black, you can see the solid black is the closest like the closest circle that we're integrating, so it's 12 parsecs of diameter. And you see that there's a very strong nebular emission. There's still some broad emission from the star, so we can still detect the star here. But what happens when we go to 24 parsecs? So here there's still nebular emission, but the contribution of the star is completely gone. So what does this mean? That already at 24 parsecs, integrating the whole light, we're not going to see the star, we're not going to detect the star. However, we know the star is there, right? So, okay, we know that the star is there, but is the star alone? Does it produce enough helium-2 ionizing photons in order to reproduce this nebular emission that we're seeing? And that's what we can learn from the models. So here we get the number of ionizing photons that we get from the nebular emission, and we compare them with the number of photons that we get from the stellar atmosphere models. So if the ratio is less than 1, basically this means that our star has more than enough photons to produce the nebular emission that we're seeing. And we do this with the 6 early WN stars that we have in the SMC, and you can see integrated for all these different spheres, right? And you can see that for all the stars except AB7, up to 181 diameter, our star produces more than enough photons in order to reproduce this helium-2 nebular line. However, if we check the spectra, we see that the star already at 24 parsecs, all of them, we cannot detect them. So they are undetected. So the conclusion here is that the star, even if we cannot detect it, it's still there, and it produces enough helium-2 ionizing photons, which means we should actually include them in our models. So this is, the conclusion from this part, the last part actually, is that first we have hydrodynamically consistent models, and they are actually in a good track, right? Because when we compare them with the 3D models, we see that they are actually in agreement, which is great. And then we can get with these atmospheric models insights on wavelength ranges that we would not see when we're observing. So basically, one of these applications is that the WN stars, they are very easy to hide in integrated populations, but they are very high sources of helium-2 ionizing photons, so we should include them in our models. So yeah, that's it.
Thank you very much, Gemma, for this very interesting overview of what can be done in terms of modeling massive stars in different evolutionary stages and the complexities and the great things can be done. Now it's time for questions, if the audience has any question here.
Thank you very much for this very nice insight into the very massive star range. My question goes back to I think it was in the very beginning of the red supergiant sections, when you showed the different layers, like extended atmosphere, etc. And I actually have a definition question. How is I know how in a Loma star, for example, an atmosphere or a photosphere is defined. How do you define like the extended atmosphere of a red supergiant? I think it was red supergiants.
It's from the photosphere to the region where the dust starts forming. So it's from like 1 stellar radii to around 8.
Okay, so it's an empirical, basically.
Yes, yeah. It's like when we see that there's dust grains, then we start getting like the dust contribution.
Okay, very nice. Thank you.
Thank you, Desmond. Any other questions here?
Thank you, Gemma. Very interesting. A curiosity, could you show again the density structure of the red supergiants that you assume.
Ah, yes, here.
That's what's more or less the shape of this function, and how where does it come from?
So this wind.
This wind density.
Yeah, it's the one you see here. So the big bump is the startup to the photosphere, and then we're including the wind, which is with this density. And then there's different gamma and beta parameters. We can change them, and then they will give us a little bit like shallower. And basically what we're doing is, this was based on a model from Harper from 2001, where they observe data from Betelgeuse, and then they infer a different, like a density for Betelgeuse. And then we use the same thing, and then now we compare it with our interferometric data.
Okay, and concerning the turbulence in the model, the O-star model, could you expect X-rays from these turbulent motions, or
Expect what? Sorry.
could you expect to see X-rays in the atmospheres?
Okay, to be honest, I don't know, because I'm not an X-ray expert at all. But actually, we could check that. I think for now, with the models that I'm using, I'm not including X-rays at all. But I guess we could check it. Yeah, I also think no, but to be honest, but I also think probably not, but yeah.
I think we have a question by Alexandra, so you can connect your microphone and ask yourself.
Hi, yes. Yeah, I would like to ask, what is the...
Wait a second, so I will put the microphone. Where is... Can you ask again?
So you mentioned that winds from Wolf-Rayets stars are quite dense. So I was wondering, what is the typical density range?
We are going to read it because I cannot hear you here, but it's in the chat, so maybe you can. Yeah, it's the question by Alexandra. I'd like to ask some question. What are the typical densities in Wolf-Rayet winds? Also, are there any suggested wind driving mechanisms for the supergiants? Is there one mechanism you think is more likely to be acting than others?
So for the densities, you can see it here. These are like the outer layers are the wind densities. You can see it -10, -11. And then, wait, what was the other question? For the red supergiant, so we think that it could be, well, there could be a mix of a lot of different things. But we think that it can be first, we have molecules in the atmospheres of the red supergiants, and these molecules, they also contribute to the opacity. I don't know where to look, but well, they contribute to the opacity. So especially with the molecules, they have all these like rotational and vibrational transitions that they will give us extra opacity sources. So it could be that the wind is driven by a combination of this opacity from the molecules in red supergiants, and then the pulsations, because these stars, since they are already like at the Hayashi limit, they are very convective, they are very unstable, and they could get out of the hydrostatic equilibrium and they could start pulsating. So we think that it can also be that there's some pulsations that are helping driving the wind, but even including pulsations, these opacity mechanisms and all that, we still cannot be sure, and we still don't know what's causing it, but there's a combination of things. And what was the other question? The mechanism likely more acting that, to be honest, I'm not sure. We are now thinking that this could be first because of these pulsations, and now we're thinking that it can be that there's also some extra ejections of mass that happen in these red supergiants, which is just like a temporary ejection that happens that also contributes to eject part of the wind. We We could find this if we actually see that there's some asymmetry in the atmosphere of the star, and we can do this with interferometry also, but I didn't do this for now. But we can also see if there's some like episodic mass loss. So yeah, I hope it answered the question.
Okay, so we have Wolf-Rayets who wants to ask or say
Yes, I would like to step in on this question with X-rays, yeah. So about OB stars. I mean, we know that all OB stars are observed as X-ray sources, and the X-ray emission is of the order of 10 to minus 7 of the bolometric luminosity. And this X-ray field has an effect on the emergent spectra, but only on certain places, like it produces oxygen 6 in a typical O star of intermediate subtype or so. But the number of X-ray photons has to compete to have any effect on the ionization, has to compete with the number of recombinations. And the number of recombinations squares with density, scales with the square of the density. And that means that the X-ray do not have an effect to the inner part of the atmosphere, only in the outer wind, where the density is small enough, and then the recombination can be compared with the X-ray effect. That's the reason why it has no effect on the inner.
Okay, thanks.
Thanks, Wolf-Rayets. Is there any question here in the audience or in online?
Yeah.
Savita.
Thanks for a very nice talk. Well, it's just by curiosity. It's about your stay here. So on the work with Sergio, how many stars do you think you will be adding to the, because I think you have 3 or 4 stars with the turbulence where you are comparing the effect of the turbulence. So how many stars are you hoping to add?
So for now, we made a selection and we have 13 with like O stars. So for now, I'm working on analyzing the 13 stars and see what happens.
Great, thanks.
But if things are promising, we'll have several hundred stars there. So
Yeah, so it's just like a benchmark to see.
Sorry again, I have a follow-up question on basically on the turbulence or on this mass discrepancy that you showed. Is there actually in this regime any chance to also test this with binaries, companions, where you have maybe mass ratios and can do some check in this way? Or is there no chance at all? I have no idea about the O-stars, but it seems like it could be an option if it exists, if they exist.
But the thing is, I feel like even if it's a binaries, we would still, for the star, we would still get something different. We don't include the turbulence because there's something happening in the star. So I would not help probably.
Okay, thank you.
Well, Rainer, I think
may I add a question to this turbulence issue? I mean, if I got it right, the predictions from this hydro calculations now predict really huge numbers for the microturbulence. But isn't there, on the other hand, constraints, or aren't there constraints observationally? I think recently it was a relatively big paper with a huge number of stars saying that typical microturbulences, there's a large individual scatter, but it is around 10, 20 kilometers per second. Can that be reconciled with the predictions of the Löwen people?
But the thing is that this microturbulence is not the same as this turbulence that we're talking about, and there's always a lot of confusion because I think this microturbulence is the one that you're adding at the end in the formal, right, in order to get like your spectra. But the one that we're talking about is a different turbulence. It's the one we are adding in the solution of the hydrostatic equation. So I think they are 2 different things, and people usually get a bit confused about it.
Yeah, I understand this, Gemma, but shouldn't it be in a reasonable agreement? If there is really such a high turbulence in the photosphere, then it would leave an imprint on the emergent spectra.
Yeah, but I think, so the microturbulence, it's true that it's around usually 20, and the turbulence that we are finding here, it's around, depending on the spectral type, it can be around 100. So it's very different.
I think you have Nicolas there. Maybe you want to say something directly from the modeling?
Yeah. Right.
Hi, Wolf-Rayets, Nico here from Leuven. I'm involved in the multi-D modeling effort as well. And it's true. So we find broadening of the lines, the macro turbulent broadening, we call it then, that is very similar in order of magnitude to the turbulent velocities that you need to get enough turbulent pressure to run these models that Gemma is running here.
Okay.
So yes, there is this paper by Sergio. Maybe Sergio, I don't know the year by heart, but where you plot this macro turbulent velocity that you find as a function of the spectroscopic gravity weighted flux, and we get almost exactly the same curve with our numerical models.
Is this the new paper, right? That's
Yeah, there's a paper on arXiv. If you're
why that's
interested.
on arXiv now. Yeah, sure.
Thank you.
Thank you. Yeah.
Question. Thank you, Gemma. Regarding this turbulence velocity, is there because you were saying that to fit the line profile, you could include this turbulence. You were always talking about this turbulence greater than 0. But I am wondering if this turbulence and the fact that the new fit is providing a new gravity, if there is a degenerate because of is there a unique solution, or there is different solutions? So by changing the turbulence and the gravity, that provides the same line profile.
Yeah. So there is, like, depending on the turbulence that you're including, you're changing the gravity to fit the same line. So there is a degeneracy. And actually now we're working again with actual observations, and then we're trying to find out if there's other degeneracies also, like how would they change for the temperatures and all that. So depending on the turbulence that you're adding, you'll have to then change the surface gravity to fit the same line. So there would be a degeneracy that would affect then your mass. But with like our 2D modeling, with these models from Nico and from Leuven, we actually can have now a bit of an idea of how it depends this on the spectral type, like what's the turbulence, like how it's related,
expected turbulence
depending on the spectral type of the star. Yes.
So then there is no way to derive this from observations. So there is no, the profile, the gravity may change in a different way the profile that the turbulence.
So you mean getting the turbulence directly?
And the gravity directly from the, in 2 dimensions, you will have the higher probability to a given unique solution, and then there is a broadening in both directions.
I need, I feel like now we would need then the insights from the multidimensional simulation.
But then
as a prior,
the posterior.
Because we cannot do it just from the observations.
But I think this is related to what Rainer was saying. But at the end, we have also this microturbulence that is also in all the stars. And in some sense, in cooler stars, is related to also convection and blah, blah, blah. So here could be related to this. So at the end, there has to be a perfect match between different quantities. So the prediction by the 2D models, the gravities and the masses from spectroscopy and evolution, plus this measurement of the turbulent velocity that we are obtaining also in our spectroscopic analysis. So everything has to be, at the end, coherent, but is basically what we are trying to do in these 2 months, to understand everything from a modeling point of view and observational point of view. So there will be ways, but
maybe using different lines, maybe you can get, I don't know, but
yeah, can I say even individual lines, if you have really high resolution, high signal to noise spectra, in narrow metal lines, you can really directly measure the microturbulent broadening.
Okay, no, I wanted only to comment on the possibility to use multiple lines, etc., to have a unique solution and so on. Well, the problem at the end is that you have actually 2 fit parameters to fit different things. So they are surely connected physically. They have to have a physical connection behind. but the values that you get for the different problems will never probably be the same. Would be enough if they are of the same order of magnitude as Moen said.
Yeah, plus the thing that we have the binaries in one sense, as Desmos was saying, that we have the dynamical masses, but also when we have a star, sometimes is a gainer in a mass transfer event. So then the evolutionary mass is actually not the mass because we are obtaining with single star model. So there is a mess here. So this is why we think that it's so great to have all these things together with a statistically significant sample to understand better because it has been there for decades. Okay, so maybe one last question if there is any. Yeah, the last one.
Naive question. Is there any possibility to get, I mean, from the actual mass that you can maybe measure or estimate of a given star, the initial mass of the star?
So
in cases where you have the Wolf-Rayets case, if it is coming from a different initial condition, it could be that the mass is completely different from the initial mass. So I would like to see if there is any way to estimate the initial mass from the actual.
Well, from the spectrum, no, but then that's why we need these evolutionary tracks to trace it back and see what was the initial mass at the beginning. And if the evolutionary masses are not in accordance, then we're not going to get accurate like initial masses, right? So I'll be here for a while. So if people want to talk about anything, I'm very happy to discuss things.
Or bringing ideas. Okay, thank you very much, Gemma, and thank you everybody here and also those who connected online. And yeah.